Hi, I know you are curious regarding what you saw in the thumbnail to understand what it is and how it works. That's why you entered into the video. So yeah, I'll just keep it very casual, plain simple, just get directly to the point. So what is this robot? I named it Saffra. Saffra means Spanish for the crop saffron. And why did I make this robot? Because saffron is the most expensive crop or expensive spice in the world. In order to harvest that particular spice, it needs really skilled laborers who does extreme precise plucking of the stigma within the saffron, because saffron is a very small plant. To do that, there have to be really efficient and skilled laborers, which is lacking to a certain extent. So recently I met with a requirement to make this particular product. That's why I came with this concept of, you might have heard this term called precision farming. So it already existed throughout the years, but the companies like John Deere, take an example in India, Mahindra, they already manufacture farm related products. But when it comes to precision farming, there are extremely delicate and advanced components and advanced technology according to the time being, which are being applied into the farming and agri-tech industry in order to increase efficiency and productivity. That's what basically precision farming is. This is done at the time being to increase both efficiency and productivity and to meet the demands. That's what happening inside the market right now. So to take a broader perspective, saffron is a very expensive spice. As you know, can go up to 1,000 rupees per gram of saffron, and the amount of effort it takes to harvest saffron is immaculate. To an example, it takes 150,000 flowers of saffron to meet 1 kilogram of dried saffron. 150,000 means 1.5 lakhs of flowers. It's a highly time consuming process to harvest this thing. The novelty machine which I've designed right now it is completely new. There is nothing like this in the market right now. I've did my due diligence and I've did my research. I'm not planning to make it commercial yet. Still will be an in-house product. So let me just, without wasting any time, so I thought I gave you a brief overview regarding the product which I'm planning to build. So in order to make this particular machine, I have to tell you how a saffron plant looks like and how can I harvest the stigma from it. In order to do that, I have to understand how the plant is and what's the dimension of the plant. As you can see over here, base bulb plant will be almost of 4 centimeters in diameter of a normal regular size average saffron plant. There can be 2 to 3 flowers or sometimes even just one flower within a plant. The plant can grow up to 13 to 19 centimeters in height in average. That's it. Because of that reason, it is easy to grow such a crop indoors in a very large scale. So these are the plant sizes. As you can see over here, what do I have to do in order to harvest the stigma without damaging the plant? Because I need the bulb still and healthy to make it multiply in the next year. So I need a robotic arm to pluck the stigma. And what kind of robotic arm? I need a 6 DOF robotic arm, because 6 DOF robotic arm means it can move in 6 different points. So there will be shoulder, elbow, arm, wrist. So there will be, I'm not getting into details into the robotic arm. You can learn that from different videos in YouTube. I'm not getting into the jargons of it. 6 DOF robotic arms. Okay, I already told you that the plant will be only almost 19 centimeters in height. I need a robotic arm that only have to be maximum 25 to 26 centimeters long. So I figured out the 6 DOF. 6 DOF means the amount of workspace. Workspace means the amount of area in which the robot can move in every single angles and in every single joints, even if on the full stretch, how much area the robotic arm can move. That's called the workspace. And I need the workspace to be max 25 to 26 centimeters. I don't need a bigger robotic arm than that. I mean, if we are doing it by ourselves, then we can just see what's there on the table and what's there on the flower, and we can just plug it directly. That's how our neural network works. So in order to make a machine understand that, or I have to create an algorithm that explains the machine what to plug. So I have to create a machine learning algorithm which identifies the stigma, the red part, another ML model which identifies the flower part, another ML model which identifies the bulb. I'll get that into detail later. Since it's a really tiny piece of thing that we see over here, the stigma is only of 1 millimeter in width. I have to be really careful regarding plucking the stigma. So there have to be enough light in order to find and plug the stigma. So I have to add sufficient lights over there for the cameras to understand where the stigma is. So I met with the arm part, the 6DOF part, the cameras, the machine learning model. Now I am splitting all these requirements into different parts. I'll split the first, which is basically harvesting the saffron. I'll split that into two arms. There can be one or two or three saffron strings inside single flower. I've made two robotic arms solely just to plug the stigma within the flower, and I'm using these two robotic arms just to plug the stigma. So two sorted. I'm using one robotic arm with a soft gripper. Soft gripper is something which has a origami Japanese style to it. It grabs the thing without damaging it. So I am using one soft gripper to hold the bulb without damaging the bulb. One arm for that, two arm for the harvesting the stigma, one arm for holding the saffron bulb, fourth arm. The fourth arm is used to pluck the flowers because I have to pluck each petals. Each petals, I mean the saffron petals are used to make fragrances. Okay, so that's useful, and even that can go up to 3,000 rupees per kilogram saffron petals. So I have to pluck saffron petals too. Don't mind my drawing over here. So my drawing is a bit bad, but this is just to make you understand how the machine have to look. Now I have to go into what kind of material should I use in order to do this. First I thought about using aluminium, but aluminium is actually not necessary because it's not generating much amount of heat. It's not generating much amount of anything for aluminium or any metal to handle. So it's manageable with normal plastic. That can reduce the expense to a very it can reduce the expense. Because of that reason I am using normal regular PLA, which is 3D printing plastic. So because since we are using this in a very controlled environment, it doesn't have to be highly expensive materials to in order to do this. Now we have a clarity regarding what to do. Then the next thing which came to my mind is designing the arm. In order to design the arm, I already have in my mind that I have to use a 6 DOF robotic arm. 6 DOF robotic arm means that it has one base, another shoulder, another elbow, then the end part. I just can't take any random numbers and make a robotic arm. I have to be precise regarding the length of each shoulder, length of elbow, length of the end effector, because I have to keep that in mind in order to meet the inverse kinematics rule. My requirement is to make a robotic arm with a maximum spread of 25 centimeters. So I used ChatGPT to make a rough idea regarding how long my shoulder, elbow, end effector. So I made a rough idea. So I came up with these numbers. Base have to be 4 centimeters, the shoulder have to be 10 centimeters, the elbow have to be 10 centimeters, so that I can go with easy inverse kinematics programming in future. So as I've told you, this is the CAD design based on the concept which we have derived before. I won't get into details of this entire CAD. All the miscellaneous marks that you see over here, those are joint angles. So these are separate joints. So to show you this part, I'll just make it simple over here. So all these 1, 2 and 1, 3 and 4, these 4 arms are 6 DOF arms, which means that they have 6 degrees of freedoms. 6 degrees of freedom means they have 6 different servo motors. 1, 2, 3, 4 and the base part. 5 and one more is there, 6. So in total 6 different servo motors. So the entire arm will be of 25 centimeters in length when you stretch this arm fully. When you make it fully stretched, the arm will be of almost 25 centimeters from the base to the end part. As I said, the saffron flower will only almost around 13 to 19 centimeters in total length. So I only need small arms for this thing. Alright, so this particular mechanism is applicable to every single arm that you can see over here. And the end effector that you see is very minute and very delicate piece. It cannot be 3D printed. It have to be laser cut using aluminium. 1, 2 and 3. These 3 parts have to be laser cut using aluminium. And this particular part, this is the one using for the bulb, saffron bulb. That thing have to be holded firmly. For example, this is the saffron bulb and the soft gripper that I've showed you, the star-shaped thing will come and grab on it without damaging it, because it should not be damaged. Then only it can produce the other saffron flowers for the next years. Yeah, that's how the soft gripper works. So let me just remove all the jargons over here. So yeah, so that's basically the core part of this thing. Okay, I'll show you the camera. This is the camera mount. The camera which we are using right now is Sony IMX 477. It's an Ardu cam with the lens of Sony IMX 477. Why I am using this particular lens over here? It's because I am using the processor called NVIDIA Jetson Orin Nano. Initially I thought of using Raspberry Pi 5, but Raspberry Pi 5 is not capable to manage 4 camera visuals with 4 ML models. In order to do that, I need a processor that's more powerful. So I picked the model called NVIDIA Jetson Orin Nano of 8 GB RAM, and that thing will be placed behind this. Let me explain how the algorithm works over here. In the conveyor belt, we'll keep a saffron plant over here in the conveyor belt. Okay, slowly that thing will move to the center part. Once it's on the center part, when one camera identifies, there are 4 different cameras. You can see over here there are 4 different mount for different cameras. And the camera I'll be using will be, every camera will be same RDU Sony IMX477 cameras. And this camera, so I'll explain how the algorithm works. For example, let's assume there is a saffron flower on the middle part. So what happens over here is, there will be flower on top. Two cameras, this particular arm and this particular arm. The cameras mounted on those two arms will only identify the stigma. The camera mounted over here will only identify the bulb, the bottom part. The camera mounted over here will only identify the flower petals. How this mechanism works is, let's assume there is a saffron plant in middle. These two arms will be having ML algorithm, a machine learning algorithm defined using CNN, convolutional neural network architecture. And this particular algorithm will identify the X, Y, Z values of the stigma in front of it. Let me explain it in detail to make you understand easily. XYZ matlab, to take an example, assume my face. My face within this frame is X and Y, can be plotted as XY coordinates, like a graph. Assume this frame as a graph, and my face will be on the X and Y coordinate of that particular frame. And distance of my face from the camera will be identified as the Z value. So that's done using depth estimation and stereo vision. This combined X, Y and Z value will be sent to the processor. Let's say the camera over here and the flower is on the conveyor belt. So the flower will be having a stigma, the red part. Once the ML model inside the camera identifies the stigma which is sitting over here, it will calculate the XYZ value. Z value is where the camera is from the stigma. Matlab, how much distance it has. For example, let's assume 5 centimeters. And also the camera identifies where the stigma is within the frame of this camera. So this XYZ value is sent to the processor inside this machine. That's basically NVIDIA Jetson Orin. The computation is done by the NVIDIA only. I'm just mentioning it as camera for the ease of understanding. The computation is done using the NVIDIA itself. This data is sent to NVIDIA. Then what happens over here is, NVIDIA will compute these XYZ values that I have received from the camera, from the ML model. The ML model is used to identify the stigma. The identified stigma is then, the XYZ value of identified stigma is then found out using the stereo depth fusion. XYZ values are given to the NVIDIA Jetson, and there is another module called PCA. The PCA is connected to the NVIDIA. These XYZ values will be used to identify inverse kinematics numbers. As I've told you, there are 6 different motors over here. This XYZ values will be used to calculate how much angle each different motor have to move in order to make this end effector reach to the stigma. Because we know that stigma is on the XYZ distance from the camera. We are also assuming the distance of camera and end effector as an error over here. So that's just basic calculation to be done inside the code. Based on that XYZ value, we create the inverse kinematics code, which is identifying the amount of angles which have to be sent to this particular servo motors in order to make this arm reach to the particular location where the stigma is. This thing have to be repeated 4 times. This particular act have to be repeated 4 times in order to make this entire machine functioning. That's the core functioning of this machine. Now this particular algorithm is applicable for this arm, this arm, this arm and this arm. That's basically how it works. When these 2 arms are harvesting the stigma, that stigma will be put into this thing. This particular arm is only using for the holding part. This particular arm is only using for the flower plucking part. We can manually turn on and turn off cameras. I mean the arms over here. So these are arm 1, arm 2, arm 3, arm 4. This is for the lights. This is for the conveyor belt, CB. Okay, you can see over here it's 12 volt, 30 amperes. So different components will be using different power ratings. Cameras, lights and the NVIDIA. These three will be having a different power supply. The arms will be having another power supply and screen will be having another power supply. So we'll be using a thing called buck converters. Buck converter is a thing which is used to reduce the voltage based on the user need. This is an emergency switch button. I mean, if you want to just stop it randomly if something goes wrong. Along with that, these lights can also be adjusted and moved to a certain direction according to how we want to use it. This is solely because we need enough sufficient light to hit the saffron plant for the camera to identify these saffron components without any shadows in it. These are minute, tiny parts. The stigma is only 1 millimeter thick. So in order to identify that part, we need extremely strong non-shadow lights. So the lights I've used over here is non-shadow lights with diffusers. So that's how this thing is, and all the components will come inside this conveyor belt. This works using 25 kilogram servo motors, and it's only 10 centimeters wide, this conveyor belt. This entire machine is only of almost 1 meter. That's it. Okay, it's a really small machine compared to what you see inside this thing. There's a screen over here. As you can see, the screen is solely for the calibration. In case if you have to calibrate the arm, in case if you have to calibrate the things which is supposed to perform different actions. So this screen is only for the settings and the calibration part. So basically that part is sorted using the screen, in case if you have to do something related to the UI or something. So yes, that's how basically this machine works. There is also a basket over here to put the saffron and the flower petals. So yeah, so I've just created a BOM, bill of materials, based on what all I have to buy, then what all components are required to be bought and to be created, manufactured in order to. I'll just show the screenshot over here. So the entire BOM will be of almost 1.3 to 1.4 lakhs. Yeah, so we are officially done with the first 20% of the work. So there is a weird status, not a weird statistics, but it's a true statistics which explains that a normal human worker can pluck almost 400 flowers of saffron in 1 hour. That's the speed of a normal human worker. And what I'm trying to do over here is do this entire functioning, the functioning which I have explained in the 4 robotic arms. I'm trying to make that happen under 5 to 6 seconds, because I need the conveyor belt to bring the thing to the place which is supposed to grab, then grab it, pluck it, then put it in the basket. The conveyor belt have to send the signal to the conveyor belt to move forward to bring the next piece. This entire cycle have to be completed within 5 to 6 seconds. If I'm achieving that particular thing, then most probably we'll be able to finish 640 flowers harvested within an hour. That's almost 1.5 times speed of a normal human laborer. The moment when we are trying to use it as a fleet, for example, I am connecting 5 of these machines together. So then when all those are combined together, I can easily manifold the productivity and the cost effectiveness by 10x or even 15x. That needs a lot of time and effort to build that particular thing. So that was the basic concept of this particular thing. I met with a requirement of what's happening within this industry and within this agri-tech field and precise farming industry. So I hope you guys learned something new today, and I hope you guys enjoyed the video. So yeah, thank you for watching.